In this presentation, we are going to learn about organic reactions, specifically substitution reactions. So there are two kinds that we are going to learn, SN2 and SN1. So let's talk about the kinetics of a nucleophilic reaction. So whenever we talk about kinetics, we talk about what is called the rate law. And the rate law, you will remember, is where you find out how the concentration is affecting the speed of the reaction. So if there are two reactants, then you find out which of the reactants, if you change, will change the speed of reaction. So for example, if you find something that is in which the speed of the reaction is unaffected by the change in the concentration of something, that is called zero order. Okay, so in zero order reactions, the concentration change of the reactants does not change the rate of reaction or the speed of reaction. In a first order kind of a reaction, the rate of reaction will double when you double the reactant concentration. Okay, so the speed is increasing in this case, and that's called first order. In a second order reaction is that when you double the reactant, then the rate of reaction is quadrupled, okay, in that case. So three kinds of order of reaction: zero, first, and second. These are the most common ones. So zero, again, where reactants do not affect the speed of reaction. In first order, the rate of reaction doubles when you double the concentration of the reactant. And then the second order, where the speed of reaction is quadrupled, okay, when you double the reactant concentration. So these are the different kinds of rates of reactions, and which are called order of reactions. Order of reactions will help us to explain the mechanism of the reaction, because if you are changing something, if you're changing the concentration of something and that is affecting the rate of reaction, it means it is part of the mechanism of the reaction. Okay, it's not a bystander. Okay, it's actually taking part in some of the active steps. So let's look at nucleophilic substitution reactions. What really are they? And this is still generic, okay? There's nothing specific about this. So in this case, we are talking about a species which is called the nucleophile, and you can see the nucleophile is a negatively charged species in this case. And then you have a substrate, and the substrate here is R, and R could be any kind of an alkyl group, okay, which is ethyl, methyl, or any kind of long alkane chain. And then you have a leaving group, okay, over here. So we have learned about the fact that you can have polar bonds, and so there is a polar bond between R and X, because X is generally a halogen, and so there is a polar bond over here. And so when the nucleophile will attack the R group, which is the alkyl group, then the X, which is the leaving group, is going to go away. So which means what you have done is you have substituted the leaving group with the nucleophile. So now in the product, the nucleophile is what is attached to the R group, organic compound, and X minus is the leaving group. Okay, so you can see the nucleophile is negative and the leaving group is negative. Okay, and then here you have the substrate. So this is kind of what it is. Here are some examples. So I want you to look at the pink color. The pink color substances here, these are all going to be our nucleophiles. These are all negatively charged. And then you have the alkyl groups over here and the halogens over here. Usually halogens are very good leaving groups, and we will talk about that as we learn more about substitution reactions. The most important thing is that this bond between carbon and iodine, or carbon and bromine, it should be a polar bond, okay, so it's easy to break. Otherwise, why is this reaction going to happen? And then what happens is, during the reaction process, is that the hydroxide will kick off the iodide and form a bond with carbon. So of course, you know, there is a whole lot of discussion about what really happens first. Does iodine leave first? Does the hydroxide attack the carbon first and then the iodine leaves? What happens first? Okay, and this is what is explained by the order of reaction. That is why we study these things. Okay, so now that you know what substitution reactions are, let's go forward. So we'll deal with the SN2 reaction first. SN2 reactions, let me give you the breakdown for SN2 reactions. So the 2 here stands for second order, S stands for substitution, N stands for nucleophilic. So don't forget that you have the nucleophile, okay, and the nucleophile is attacking the substrate, and the substrate has the leaving group. Okay, so the substitution that is happening is this substitution that we are talking about. Okay, so that's the substitution, and so then X is of course gone. Okay, in this case, so that's the substitution that we're talking about. So now the 2 over here, okay, so what the 2 indicates over here for a second order, it means that it is actually a bimolecular reaction. So what does bimolecular mean? Bimolecular means that both of these things, the nucleophile and the substrate, is involved in the rate determining step. Okay, so we were talking about, that the mechanism of the reaction will tell us how the reaction works and what is involved in the transition state. So that's what we are going to talk about here. We will come back to the inversion of stereochemistry in a minute, okay, when I talk about the characteristics of SN2 reaction. So let's see what an SN2 reaction looks like. So this is kind of gives you a little kinetics, so it takes you back to Gen Chem 2. It talks a little bit about the kinetics of the reaction. So here you have the substrate, and then here is the nucleophile, and here's the product, here's the leaving group. So generally, if you remember from your Gen Chem 2 kinetics work that you did, is that you keep one thing constant. So here you have two reactants, right? The substrate and the nucleophile. So you change the concentration of the substrate and you keep the nucleophile constant and see what happens. And you can see that the reaction rate has changed. And then you keep the hydroxide constant, then you keep the substrate constant, so 0.001, 0.001, and you double the hydroxide, and then look what happens. You also double the rate of reaction. So which means that if you're changing both of the concentrations of the substrate and of the nucleophile, the rate is doubling. It is changing. Okay, and because it is doubling, it means that it is first order with respect to the substrate and with respect to the nucleophile. So this is the rate equation at that point then. So rate is equal to K, and then it involves the substrate as well as hydroxide. If the order of reaction is 1 for each, we don't have to write the number 1. Okay, otherwise we generally would go ahead and write the number right here if it is 2 or 3 or something. But if it's 1 or 0, of course it will not even be part of the rate equation. But if it's 1, we don't write 1. Okay, so this rate tells us, this kind of a reaction or experiment tells us that this is the rate equation. The rate equation tells us that the rate is dependent on both the substrate as well as nucleophile. Okay, so fine. If it is dependent on both, what does that mean for us? Okay, what does that mean as far as the mechanism is concerned then? So what it means for us then is that the Cl doesn't leave first. Okay, so here you can see in the mechanism that the hydroxide is attacking the carbon, which has the leaving group. So this is the polar bond. So you can see the delta positive and the delta negative on the chlorine. So delta positive, which is the electropositive center, then the carbon. So the hydroxide, which is negative, is attacking attacking the carbon, which is delta positive. And at the same time, the chlorine is trying to leave. So the transition state is kind of this looking thing where you have a bond formation going on with the hydroxide or with the nucleophile, and you have a bond breaking going on with the leaving group. Okay, so both the things are happening, and that is why the rate is dependent, or the rate of reaction is dependent on both things, because both of them are taking part in the transition state. This transition state is represented by the square brackets and of course this symbol over here. Okay, so whenever you see that kind of a symbol with square brackets, you will know that this is a transition state. Eventually what's going to happen? Well, the leaving group is going to go away and the hydroxide will be attached to the carbon. Okay, so this is kind of what the mechanism is. So what does the bimolecular tell us? The bimolecular second order reaction tells us that both the nucleophile and the substrate are going to be part of the transition state. Okay, so this is kind of what is involved. The other thing I want you to look over here, because we're going to talk about it later, is look at the way the nucleophile is attacking the carbon. It's actually coming from behind. Now remember, carbon is a tetrahedral. Okay, so which means that the bond angle here is about 109. So it's like an umbrella, So if this is the handle of the umbrella, then the hydroxide is coming from behind, okay, in there. So that is how this kind of an attack is going, all right? This is going to be important for us later on. So here is the energy diagram for us to understand. So you have seen these kind of transition state diagrams before. So here is the starting materials, the reactants. For us, the transition state involves both the nucleophile and the substrate. And then of course, there is a free flowing down here because the last step is going to be easy to do. The initial steps are hard to do, which is called the rate determining step then, which involves course the energy of activation or activation energy. So then the last steps are not all that hard because at that point you're forming the product. Okay, so this is the energy diagram. So you only have one transition state here. So this is a one-step reaction, okay, as you can see from the transition state, all right, and of course the transition state is going to be the highest in energy. So I said to you that the backside attack is going to be important for us, and that is important because of the stereochemistry in SN2 reactions. So I said that hydroxide is attacking the backside. So if you have a chiral center here with the carbon, so when you're attacking something in the backside, what really happens, and I gave you the example of an umbrella, the umbrella will kind of flip. So if you keep watching this and watch it like a movie, then you can see that the umbrella is flipping. The CH3 has moved a little bit. The C6H13 group here, that has moved a little bit. So all these groups are moving and the umbrella is flipping very slowly to the other side. So bromine now has left in the product and hydroxide has attached over here. So you started with one configuration of carbon here with the stereo center of R, and then you ended up with something which is S. Okay, and that is the product. Why did that happen? That happened because the transition state involves both of the starting materials in there, the nucleophile and the substrate, and there's also a flip going on because of the backside attack. So both of these things contribute to what we call inversion of configuration. So inversion of configuration means you go for, if you start with R, you'll end up with S. If you start with S, you'll end up with R product. Okay, so this is something you have to be aware of when you're doing SN2 reactions and you have a chiral center. So that way you can be assured of what kind of product you're going to get, because stereochemistry is important when it comes to chiral centers. All right, so this is the bottom example. It's a little bit easier to see because in this case now what you're seeing is something which is that you start with cis, where you have the both hydrogens on the same side, and here comes the hydroxide coming from the backside. Chlorine is leaving, so now hydroxide is attached to the backside and the hydrogen had to flip over. So you started with something that was cis and now it is trans in the product. So that also is an inversion of stereochemistry. Okay, so this is an important characteristic of an SN2 reaction. So here are some examples of SN2 reactions. You can look at all of these at your own convenience and time because there are so many more reactions. And essentially what you're looking for is the nucleophile. Okay, so in this case, hydroxide is the nucleophile. Then you're looking for the substrate. In this substrate, you're looking for that carbon that has the leaving group. Okay, and so those are the main things you're looking for in a reaction. Now, what is the purpose of sodium? The sodium is what we consider to be the spectator ion because it's on both sides and it provides the counter ion. There is absolutely no solution out there which is just made up of hydroxide ions. So even though we write hydroxide ions, we just don't really mean hydroxide ions because there has to be a counter ion. And the counter ion can be sodium, potassium, whatever monovalent ion to balance that hydroxide out. You can use calcium also, that's all right. That'll just give you 2 moles of hydroxide, that's all. But it has to have a counter ion. Sometimes we don't write the counter ion because it's kind of understood, so we don't write it. But otherwise, if it's written, don't get confused, okay? Because the sodium is not really taking part in the reaction. As I said, it's a spectator ion. Okay, so in this top example, it's sodium hydroxide. That is the nucleophile. So the nucleophile is hydroxide, really, not the sodium. And then in the bottom example, you can see that we have a neutral nucleophile. And in the case of a neutral nucleophile, what you have is an electron-rich nitrogen. So you have a lone pair of electron that is going to do the reaction. So in this case, what happens? You don't have a counter ion, right? So when you get to the product, you end up getting something which is a charge then, okay, which has a formal charge. And so then bromide, which is the leaving group, that becomes the counter ion. Okay, so one of the things you will have to get used to in organic reactions is trying to understand, okay, this is just the counter ion, this is not taking part in the reaction, or this is the leaving group, or this is the spectator ion. So you don't get confused by all these other ions in there. And you also need to understand and focus on what reactants are really reacting here. So what are the uses for SN2 reactions? Unbelievable. Okay, there are so many, because the main thing you can do with them is form all sorts of functional groups. Okay, so here you have a list of substrates, which could be anything, you know, and right now it just says R, but it could be anything in there. We will talk about exceptions later on, so you'll know what you cannot use as a substrate, but otherwise in general you have a large choices of substrates to use, and then you have a leaving group on there, and look at the nucleophiles. I mean, pretty much you can choose anything that is electron rich, and that will give you a product. So you can make any kind of product you want to make. So it really opens up all sorts of doors for you, for reactions, for products, for doing synthesis and whatnot. So they're highly functional reactions. Now let's talk about SN1. Now that you understand SN2 reaction, hopefully SN1 will be a little bit easier for you to understand. So first of all, this is unimolecular, hence the 1, okay, in there. The N still stands for nucleophile, the S still stands for substitution. But the one thing is important here, because that says that it's a unimolecular reaction and still nucleophilic substitution. So in this case, we are going to see that it's actually a two-step reaction with a carbocation intermediate. And we'll talk about the rate of reaction and such in the next slide. So here is what happens with the SN1 mechanism. And I know this slide looks a little bit busy, but here, just focus with me and you'll be fine. So here is the substrate, okay? And the substrate is, of course, the R group over here. And then you have the Cl over here. This is the nucleophile. So remember, your nucleophile can be negative or it can be neutral as well. So in this case, it's a neutral one, okay? And so then the product has the OH on it. And if you're wondering, where did the OH come from? Well, H2O is actually HOH. So the OH part here, that is what is attached on this side. So HOH, water in general, as you know, is not going to be ionic. It's also not considered to be either acidic or basic, because it's an amphoteric substance, okay? But that is the characteristic of this reaction. The way it works is that even water can react, okay, which is not negative or basic in any way. So let's look over what happens, okay, in this case. So the first step that happens in case of an SN1 reaction is that the chlorine leaves. In SN2 reactions, the chlorine did not leave first, okay? It was the nucleophile that attacked, and then you formed an intermediate with the nucleophile and the leaving group. In this case, the leaving group is going. So here's the chlorine saying bye-bye to the substrate, and then here you have the substrate. This is an important thing, because right here you just formed a carbocation, okay? And carbocation is a positive version of the carbon because it has less electrons. Why does it have less electrons? Because the chlorine took the electrons with it, okay, when it left. So chlorine has the electrons, so carbon is left without it, so carbocation, all right? So that's step number 1. If you want to follow with the graph, here is the transition state graph also with this. This graph is a little bit more busy than the one for SN2. So here is the first transition state, okay, where you form the carbocation. You can see it's also the most highest energy level transition state, which means this is the rate determining step, okay, because this takes the highest amount of energy. Once the leaving group is gone, now you can have the nucleophile attack. Now in this case you have water as a nucleophile. You can also have hydroxide as a nucleophile. It's not that you have to have water. So if there was hydroxide as a nucleophile, your transition state graph would look very different. I'll talk about that in a second, okay? But let's talk about water first. So water is attacking over here. Now it's the electrons and the oxygen, they are negative. So they attack the carbocation, and they form this bond over here. Now this is the new bond that's formed. Oxygen now has 3 bonds, hence the positive charge, okay, because now you have a formal charge of +1 on oxygen. The last step is then where this oxygen is going to get deprotonated. So another water molecule comes by, picks up a proton, and you finally have a product that looks like the product, which means it's neutral and a kind of happy looking product, okay, that you were hoping for. So this is kind of what happens in an SN1 reaction. So basically the most important thing here that you need to know is that you form the carbocation, okay, in this case. This is the transition state. Now, if, as I said, if this was hydroxide, okay, so for example, if this was your carbocation and you had a hydroxide coming in and this was it. So in this case, what's happening is you don't really have an extra transition state. So in this case, you will just have the 2 transition states, one for the carbocation and then one for the hydroxide attacking. Okay, in this case, you have 3 because there are 3 steps in this reaction. Okay, so don't get too bogged down by transition states if that's bothering you, or you can always ask me about that. But the most important thing is, of course, the carbocation formation. So here's the energy diagram. I just explained it to you. So hopefully you will understand this a little bit better. So there are 3 transition states or 2 transition states depending on what kind of a nucleophile you have. Okay, so it can change. It doesn't always have to be 3. You can't memorize this. So the stereochemistry of SN1. So when we talked about SN2, we talked about the backside attack, the flipping, and inversion of stereochemistry. R goes to S, S goes to R. So in this case, what happens is that you end up in a different kind of stereochemistry with SN1. Why? So here you have the carbon, and this is a chiral carbon. You can see that there are 4 different groups on this carbon. So once the bromine leaves, okay, with its electrons, so here you form a carbocation. So once the carbocation is formed, suddenly what happens is that you change the shape of the molecule. So this was a tetrahedral before, but now what you have, it is a trigonal planar carbocation. Trigonal planar means that it's in a plane, and if it's in a plane, that means that the nucleophile can attack either from the top or from the bottom, okay, because planar means it's like a, you know, on one plane, 2-dimensional, not 3-dimensional. So if it's 2-dimensional, then, you know, the carbon is exposed, and so it can get attacked by the nucleophile from either on the top side or on the bottom side. It doesn't matter, there is no preference, okay, because both sides are completely available. So in this case, what happens is that you end up getting a racemic mixture, all right, so which means you'll have a 50% S and a 50% R. So no matter what you start with, whether you start with R or S, your product is still going to be a racemic mixture if you're going to follow the SN1 mechanism. So you can see it's really important for us to know which mechanism we are dealing with, because the stereochemistry of the product is going to change. Now, if the stereochemistry of the product does not matter to us, then this is not important, okay, whether it's SN1 or SN2, although it's still important for us to know in order to control the reaction, but at least not as far as stereochemistry is concerned. Okay, so if you want to be very specific about what kind of stereochemical product you get, then it's really important for us to know what kind of mechanism we are following. So in this one, I hope you learned a little bit about the substitution reactions, what a nucleophile is, what the electrophile is. Nucleophile is negative, electrophile is the positive center, leaving group is what's going to go away. First order is unimolecular and second order is bimolecular. Then we talked about transition states, and 1 for SN2 and 2 to 3 for SN1. Then we have, of course, the rate determining step, which is the slowest step, okay, for all the reactions. And then we talked about carbocation, and carbocation is in SN1, not in SN2. And finally, we also did talk about the configurations. Okay, so inversion of configuration or retention of configuration. So retention is when you get the same one, which you really don't, because in SN1 you actually get a racemic mixture. So even if it's retention, it's only half of it. Okay, so in SN2 you have inversion and such. So this is, I hope, what you have learned from this presentation.